In this video, I want to talk about something called variation equations. Okay, so let's look at a couple definitions. We say that y varies directly with x when we have the following equation. Okay, we have y is equal to kx, where k is some constant that is not equal to 0. Or in plain English, what this is really saying is that y gets, assuming k is positive, y gets bigger as x gets bigger. That's really what we're saying here. Or if k is negative, I guess y would get smaller in the negative sense, I guess, as x gets bigger. But let's just pretend k is positive. As x gets bigger, y will get bigger. Okay. If you think about the number line, as x moves further away from 0, y will move further away from 0. That's probably a more general way of saying it. Okay. And now we have another type. If y varies inversely with x, then we have the following equation. Y is equal to k divided by x, where k is some non-zero constant. Okay. And so what this is saying is that as x gets bigger, y is actually going to get smaller. Okay, so as we divide k by some bigger and bigger number, y is going to get smaller. Okay, and as x gets smaller, y is going to get bigger. So as x gets closer to 0, y is going to get bigger. This describes an inverse relationship. Okay, so let's look at how we might be able to write a direct variation and an inverse variation equation when we're given a little bit of information. So here it says we want to write a direct variation equation that relates x and y when y equals 27 and x equals 3. Okay? So if we remember, our direct variation equation is y equals kx. Okay? And if we want to find k, we can go ahead and plug in our x and y values. Okay? So if we plug in our x and y values, we get 27 is equal to k times 3. So we can divide both sides by 3, and we'll get that k is equal to 27 divided by 3, which is just 9. So k equals 9. So our direct variation equation is going to be y equals 9 times x for this particular relationship. Okay? So pretty easy, right? Not too bad. That's a very quick, very direct, no pun intended, very direct way of solving this problem. Okay. How about if we want to write an inverse variation equation that relates x and y when where y is equal to -4 when x is equal to -6. So our inverse variation equation is y is equal to k divided by x. And again, if we want to find k, we can just plug in our x and y values. So we can have -4 is equal to k divided by -6. We can multiply both sides by -6. Okay, these will cancel. And we get that k is equal to -4 times -6. Or we can say that k is equal to positive 24. So therefore, our inverse relationship can be written as y equals 24 divided by x. Okay, and in your homework, it'll ask you to find what y is equal to and x is equal to something. And for each of these, you can just plug that value in for x. But I feel like that's pretty straightforward. If you have any questions about it, feel free to let me know. Okay, um, I guess we can do one real quick. So if we want to find out what 24 is going to be, or sorry, what y is going to be when x, so when x is equal to, we'll say 8. When x is equal to 8, we have y is equal to 24 divided by 8, which is just 3. So we would say that y equals y equals 3 when x equals 8. Okay, and hopefully you can see as x gets bigger, y is going to get smaller, right? If we said x was 24, we'd have 24 divided by 24, and we would get 1. If we said x was 48, we would get 1/2, and you get the idea. As x grows, y is going to get smaller. Okay. So there's another type, kind of another type. It's more or less a more advanced form of a direct variation equation. We say that y varies jointly with x and y when y is equal to k times, or x and z, I'm sorry. Y varies jointly with x and z when y is equal to k times x and times z, okay? Here again, k is a non-zero constant, okay? And in these next few, we're going to use this and our previous two to try and write equations that model certain relationships, okay? So here we want to write an equation that models the following relationship. P varies jointly with the square of D and the cube of U, okay? So when we say the square of D, we can think of this as just D squared, okay? Yeah, not something you want to overthink here, okay? And same thing for the cube of U, we can write this as U cubed, okay? So if we say that P varies jointly with the square of D and the cube of U, we can use our joint variation property here, where y is equal to k times x times z. So we can write this as, here, P varies, so P equals k. We don't know what k is, and we're actually not given enough information to find out what k is here. But k, or at least not in a numerical way. But k is equal to P is equal to k times d squared times u to the third. Okay, so that's how you would write that. And the next one here, we have that w varies directly with the cube of u and inversely with d. Okay? So the way I like to think of this is to kind of break this into two separate parts. So if we know that w varies directly with the cube of u, we could write this as w equals k times u to the third. But if it also varies inversely with d, we could just divide this by d, okay? So the idea here is that you can find some constant that would make this, if you were given more information, you could find some constant that would make this this relationship work here, okay? So really, these are quite simple. They're not too bad. Sometimes you got to just think about them and just try to remember all of these three different rules about your joint variation, inverse variation, and direct variation. These shouldn't be too bad to figure out, but sometimes they can be tricky. So as always, if you have any questions at all, please email me and I can try and help you out.